Hi students, how would it be if light could actually bend around a wall? Wouldn't that be fascinating? That is what we're going to study about in this chapter. This chapter, which deals with the bending of light rays, is called diffraction. Let's proceed with this fascinating phenomenon. So what exactly is diffraction? Diffraction is the bending of waves around an obstacle such as the edge of a slit. You see, generally we observe that sound bends around walls and it bends around obstacles to reach us. For example, if you have a friend in another room and there's a door open, you'll be able to hear him clearly because the sound will travel, through the door and it'll reach you. In that case, you won't feel that there's a wall between you two people because the sound will travel through the door even though there's a wall. However, you cannot see the friend because it seems that light waves cannot travel through the door. For example, if this is the door, this is the wall, and your friend is on the other side of the wall, and this is the door, and your friend is somewhere here behind the wall, okay, and you are here. Now you know that you cannot see your friend because light waves won't bend like this and come and reach you. That won't happen. This is a common experience, but sound waves do that. Now this bending around walls is what is called diffraction. If there's an obstacle in the path of a wave, there's an obstacle like this, then if the wave bends like this and travels like this is what is called diffraction. Now the interesting part here is that we are going to study diffraction in light waves in this chapter, and we already know that this doesn't happen. Light waves don't seem to bend around walls. But what we see is that at the microscopic level they do. When the obstacle is approximately of the same size as the wavelength of light, or say 5 times the wavelength of light, in that case light waves actually bend around the obstacles and reach you. This is a very interesting phenomenon. So what this means is, if the height of this wall was of the order, say 100 nanometers, and this door was such that the width of this door was say 50 nanometers, if that was so, then light would actually bend and reach you. So if we condense the universe, if we made the universe a very small place of very small dimensions, in a baby universe in which everything was of the size of nanometers, in such a universe you would actually be able to see your friend even though he would be on the other side of the wall. That is what diffraction is all about. Isn't that interesting? That you would actually perceive a friend standing on the other side of the wall because light waves coming from him would travel through the door and reach you. Just imagining it is giving me the goosebumps. So some scientists have performed experiments to actually look at exactly how the light waves bend, exactly by what amount they bend, all these things. So that is what we're going to study in this chapter. We're going to take a slit of very small width and then we're going to see how light gets diffracted through that slit. So shall we proceed? Here we go. So for example, if this is a very small slit and a light beam strikes the slit, this is how it spreads. Now as you can see, had light traveled only in straight lines, in that case the light beam would have proceeded like this, correct? It wouldn't have gotten diffracted or distracted in any way. But the light here does bend towards this side. The light here does bend towards this side, and that is how diffraction takes place. However, as I just mentioned, the size of this slit should be comparable to the wavelength of light for diffraction to occur. Before we study exactly what dimensions the slit should have, or before I derive any formulae related to diffraction to see how much the light bends, let us first see how diffraction actually occurs. To make it very simple, let me consider the example of a stone being thrown inside a pond. Imagine that this blue thing that you see on your screen, the blue surface, is all water. So when I throw a stone into the water, a ripple is created, isn't it? And the ripple just keeps on expanding like this, correct? There's no doubt about it. Now imagine that I'm dropping 8 stones at the same time in water. then ripples like this will be created, correct? So many ripples. Now if you look carefully, if we join the ends of each ripple as shown, all of these ends will actually line a straight line. What I mean to say is that as these ripples move forward or they expand inside the water, this straight line keeps moving from left to right. I know that's a bit difficult to imagine, but just, visualize ripples being formed. I'll repeat, the tangent to all these ripples will actually keep moving from left to right as these ripples expand. These ripples are actually wave fronts. Can you make that out? You see, when you drop a stone into the water, waves are formed like this, like this, like this, like this, in all directions. And when you join all the points with a similar amplitude, we had discussed this in the chapter waves. When you join all the points with a similar amplitude, you get a wave front. And it is these wave fronts that we observe to be moving when we observe the ripples. So now the line that is tangential to all these wave fronts, that also appears to be moving from left to right as these ripples expand. So as these ripples keep expanding, the line here keeps moving from left to right, and as it moves, it encounters this slit of ours. Let's see what happens as it encounters this slit. The line becomes a curve. Did you understand exactly what's happening here? As soon as the straight line struck this slit, it got bent and it became like a curve. So when the straight line was striking this slit, the wave fronts were like this, intermingled with each other, and this line was tangential to the wave fronts like this. So this is how the wave fronts were when this line was approaching the slit. The ripples, this is how the ripples were. Now as soon as this line strikes the slit, the line gets bent and the wave fronts are then like this. This line is still tangential to the wave fronts, but then it's a curve now. It's not a straight line now. It's like this. So you can see this is exactly what happens to light waves as they pass through a slit. The wave fronts orientation, the angle between the wave fronts changes, and this line that is tangential to the wave front, it gets bent, and as it gets bent, you can see the ripples still keep expanding in all directions, and therefore light actually keeps traveling in all directions like this. That's exactly why light gets bent. This principle that I just showed you, is called the Huygens principle. You must have already heard of it. And the Huygens principle is a very effective way to explain diffraction, because as you can see, because of the bending of this tangential line, you can see that the ripples are now expanding in different directions instead of, expanding in this particular direction. And that is what causes light waves to propagate in different directions after passing through a slit. Like this. Now let's see how this pattern changes when you increase or decrease the diameter of the slit. Remember I had said that the slit should be of the order of the wavelength of light for diffraction effects to take place, for the light to actually get bent. As you can see here, the light is getting bent. After all, the straight line is turning into a curve. Now if you further decrease the diameter of the slit, in that case the light will get bent even more, isn't it? That is obvious. And so greater diffraction will take place when the size of the slit is smaller. If the size of the slit is very large, in that case there will hardly be any bending, as you can see. Correct? That is the reason, if you actually take a hole a few centimeters wide, hardly any diffraction effects will be observed, because the tangent to all the wave fronts as it comes traveling towards the slit, it virtually passes unchanged if the size of the slit is very large. I know all this might actually seem quite vague to you, but if you've just got the essence of it, if you've got exactly what is happening, how the wave fronts are traveling such that the tangent to the wave fronts is a straight line, and how the straight line is getting bent as the waves reach a certain slit, if you just get this concept, that's enough at this particular level. It's enough for competitive examinations at this stage. Okay, so let's now delve into some more details and find out exactly how diffraction takes place, exactly by what angle the waves are bent after passing through a slit. Let's perform some calculations using some diffraction formulae. So let's consider a slit of width b right here, and let's make light waves come and pass through the slit. Let's place a lens in front of the slit which focuses all these light waves on a screen. First of all, observe these two rays here, this one and this one. This first ray is the ray that is passing just next to the edge of the slit, and this ray in the middle is the ray that is passing at a distance exactly b by 2. So it's passing through the center of the slit, and this wave is passing just at the end of the slit. Now at this middle point, that is just opposite b by 2, the path difference between these two waves will be 0. I know that this will be the hypotenuse of this triangle and this will be one side of this triangle, but then if the size of the slit is small, you can assume that this distance is equal to this distance approximately. So if you consider waves coming like this, all of them will have 0 path difference at this particular point, correct? So just as in the case of Young's double slit experiment, where you had 2 slits and the path difference in the middle was 0, there was a central maxima, remember? In this case too, there will be a central maxima. The only difference is that in Young's double slit experiment, there were only 2 slits. In this case, there are infinite slits, here, 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 very near each other. And the light waves coming from all these slits will interfere constructively at this point because there is no path difference between all these light waves. So definitely there will be a central maxima at this point. There is no doubt about it. Correct?